Hello friends, welcome you all to the 27th lecture on function analysis and its application. In this lecture, we will discuss the inner product space with examples. This is the content of today's lecture, inner product space with examples. Inner product space. Definition. Let X be a linear space over the field F. A function, this is the notation of inner product, this is the function. A function this such that X cross X to F is said to be an inner product on X if it satisfies the following conditions. First, inner product XX always non-negative, that is inner product of xx greater or equal to 0 for all x belonging to x. And if inner product of xx is equal to 0, if and only if x is equal to 0 vector. Second, inner product of xy equal to conjugate complex of the inner product of yx for all xy belonging to x. And for alpha scalar, then inner product of alpha xy equal to alpha into inner product of xy for all xy belonging to x. And inner product of x plus y z equal to inner product of xz plus inner product of yz for all xyz belonging to x. The scalar xy, inner product of xy is scalar because if x is the element of x and y is the element of x, then function that is inner product xy is the element of f. Then the pair x and function inner product is called the inner product space or pre-Hilbert space. Some observations of inner product. First, inner product of xx is a real number. Explanation. We know that by second property xy is equal to conjugate complex of yx. Okay. So here if both element is same, that is y is equal to x. Therefore, inner product of xx is equal to inner product of xx bar. That is a real number because we know that if z is a complex number and z is equal to z bar, then z is real. Okay, so this is the number, real or complex. So suppose this is a complex number and this one is equal to same as conjugate complex. Okay, that is z is equal to z bar. Okay, then inner product of xx is real number. Second, if alpha beta be scalar and x, y, z belonging to x, okay, then inner product of alpha x plus beta y z equal to alpha inner product of xz plus beta inner product of yz. Explanation. Since inner product of alpha x plus beta yz equal to inner product of alpha x z plus inner product of beta yz using property 4. Okay, and using 3, this one. So this can be written as alpha into inner product of xz plus beta into inner product of yz. That is, this one is true. Similarly, inner product of alpha x minus beta y z equal to alpha inner product of x z minus beta into inner product of y z. Explanation. Since inner product of alpha x minus beta y z, it can be written as alpha x plus minus beta into y z using this property, that is inner product of alpha x z plus inner product of minus beta y z. Again using third property of inner product, that is alpha into inner product of xz plus minus beta into inner product of yz, because alpha and minus beta are scalars. Therefore, this can be written as alpha into xz and this one minus beta into inner product of yz. So this equal to alpha into inner product of xz minus beta into inner product of yz. Okay, so it is true. Third, inner product of x alpha y equal to alpha bar into inner product of xy. Explanation. Since inner product of x alpha y equal to conjugate complex of the inner product of alpha y x. Okay, using property 2. This one. So this can be written as this. This is the scalar. So using property 3, so alpha y x can be written as outside the alpha. So this is inner product of alpha y x bar equal to alpha y x bar. Okay, this can be written as alpha bar and y x bar, this one. And again using property 2 of inner product, that is inner product of xy. So inner product of x alpha y equal to alpha bar inner product of xy. Fourth, inner product of x alpha y plus beta z equal to alpha bar into inner product of xy plus beta bar into inner product of xz. Explanation. So inner product of x alpha y plus beta z can be written as conjugate complex of the inner product of alpha y plus beta z x by property 2. And again using property 4, this is type of x plus y z. So this can be written as conjugate complex of the inner product of alpha y x plus inner product of beta z x, and this can be written as conjugate complex of inner product of alpha y x plus conjugate complex of the inner product of beta z x, because both term as a complex number or real number. Okay, so we can write z1 plus conjugate complex of the z1 plus z2 is equal to z1 bar plus z2 bar. Okay, so using this property, this can be written as this. Again applying property 3, so inner product of alpha y x can be written as alpha outside the inner product and whole conjugate complex, then alpha bar into conjugate complex of the inner product of yx. Similarly, this one beta bar into conjugate complex of the inner product of zx. Again, using property 2 of inner product, we can write this expression as alpha bar into inner product of xy plus beta bar into inner product of xz. So this is proved. Similarly, inner product of x alpha y minus beta z equal to alpha bar into inner product of xy minus beta bar into inner product of xz. Fifth, inner product of 0x, that is 0. Why? Here 0 is as vector. Since inner product of 0x can be written as 0 as scalar product of any vector y. Inner product of 0 into y and x. Again, applying the property alpha x y equal to alpha xy. So here alpha is 0. So we can write 0 into yx, that is 0. So inner product of 0 and any vector x, that is 0. Similarly, inner product of alpha x beta y equal to alpha beta bar into inner product of xy for all xy belonging to x and alpha beta belonging to F field. Okay, so alpha x beta y can be written as alpha x beta y. So this can be written as alpha x beta y. Again, applying this property, we can write alpha beta bar xy. Okay. So we have this one. Next, if inner product of xy is equal to 0 for all y of x, then x is 0. Explanation. Let xy is equal to 0. This is for all y belonging to x. So then taking y is equal to x, we get inner product of xx is equal to 0. And we know that by first property, if inner product of xx is equal to 0, that is x is equal to 0. Okay, so it is true. Note that if X be a linear space over the field F is an inner product space, then it is called a Euclidean space if F is the field of real numbers. Also, this is called the unitary space if F is the field of complex numbers. Example of inner product space. First example, the L2n space is an inner product space. Let x1, x2 and so on xn, and y also is the n tuple of y1, y2 and so on yn, both belonging to L2n. Define the inner product of L2n as follows. Inner product of xy equal to summation I is equal to 1 to n xi yi bar. Equation 1. We show that all conditions of an inner product hold in equation 1. Proof. First property, here 4 property of inner product. So we have to check one by one all conditions of inner product. So first, inner product of XX. Here inner product of XY defined as this. So inner product of XX is equal to summation I is equal to 1 to n xi bar. So xi as complex number, that is x into xi bar, that is mod xi square. Okay, that is summation I is equal to 1 to n mod xi square. This can be written as norm of x square. We know that norm x always non-negative, that is greater or equal to 0. Okay, or this is sum of the n term of positive numbers. Okay, so summation of all terms always greater or equal to 0. Therefore, mod xi square greater or equal to 0. Thus, from equation 2, sum of n non-negative real numbers, then inner product of x greater or equal to 0. Also, if inner product of xx is equal to 0, inner product of xx defined summation I is equal to 1 to n mod xi square is equal to 0 by this. This is the modulus term, and sum of square of the modulus term of n time equal to 0. So each mod xi square is equal to 0 for all I 1 to n. Taking the square root of both sides, that is mod xi equal to 0. So this is modulus term of xi is equal to 0. It means xi is equal to 0 because modulus always non-negative. Okay. So xi is equal to 0 for all I 1 to n. It means x1 is equal to 0, x2 is equal to 0, and so on, xn is equal to 0. This implies that x is n tuples of x1, x2, and so on, xn. So as per this, each xi 0, that is x is equal to n tuples of 0, 0, 0. That is 0 vector. Okay. Hence, inner product of xx is equal to 0 if and only if x is equal to 0. So first condition of inner product is satisfied. Second, we have to prove conjugate complex of the inner product of xy equal to inner product of yx. Okay. So here conjugate complex and inner product. So putting the value of inner product of xy from the statement, this. Okay. Then we can write this. And this can be written as summation I is equal to 1 to n xi yi bar and total conjugate complex. That is summation I is equal to 1 to n conjugate complex of xi yi bar. Because we know that z1 plus z2 plus and so on plus zn conjugate complex of whole equal to z1 bar plus z2 bar plus and so on plus zn bar. Okay. So this, as per this property, we can write this. And here this term can be written as this. Okay. Because we know that z1 z2 bar is equal to z1 bar z2 bar. Okay. So xi bar and this is yi double bar. Okay. And we know that z bar equal to z. So yi double bar, that is yi. This is both scalar, so we can interchange the position. So this can be written as yi xi bar, that is inner product of yx as per the statement. Okay, if we interchange this y and x, so here yi xi bar. Hence, second condition also satisfied. Third, if alpha belonging to C, that is scalar, then alpha x equal to alpha x1, alpha x2 and so on alpha xn. Okay. So inner product of alpha xy, so ith place of alpha x, that is alpha xi, and yth place of y is yi. So as per the statement of inner product of this example, we can write this inner product as summation I is equal to 1 to n alpha xi yi bar. Here alpha independent of I, so we can write alpha outside the summation. So alpha into summation I is equal to 1 to n xi yi bar, and again this can be written as inner product of xy. So inner product of alpha xy equal to alpha into inner product of xy. Fourth property, if xy defined above as this and z is equal to n tuples of z1, z2 and so on zn, then x plus y is equal to n tuples of x1 plus y1, x2 plus y2 and so on xn plus yn. Then inner product of x plus y z equal to summation I is equal to 1 to n xi plus yi, because ith place of the vector x plus y is xi plus yi from here, and ith place of vector z is zi. As per the statement, we can write summation I is equal to 1 to n xi plus yi into zi bar equal to summation I is equal to 1 to n xi zi bar plus yi zi bar. This can be written as in two terms, summation I is equal to 1 to n xi zi bar plus summation I is equal to 1 to n yi zi bar. This can be written as inner product of xz and this is inner product of yz. Hence, the space ordered pair of L to n and given inner product is an inner product space. Second example, let CAB be the linear space of all continuous real valued or complex valued functions on closed interval AB for vector xy belonging to CAB. Define inner product as integral a to b xt yt bar dt. Then ordered pair CAB with inner product is an inner product space. So now we show the all conditions of an inner product of equation 5. Proof. First condition, here inner product of xy defined as integral this, that is integral a to b mod xt square dt. This is modulus value and also square, so this is mod xt square is non-negative for every t lying in the closed interval AB. Therefore, from equation 6, we get inner product of xx greater or equal to 0. Also, if inner product of xx is equal to 0, if and only if integral a to b mod xt square dt is equal to 0. Okay, so a to b mod xt square dt is equal to 0. This is mod xt square is 0. So this is modulus value square 0, taking the square root of both sides, that is mod xt is equal to 0. Okay, so here after this mod x t is equal to 0. Okay, this is the modulus value is equal to 0, modulus always non-negative, and this is 0. So if and only if xt is equal to 0. Xt is equal to 0, it means vector x 0. So inner product of xx is equal to 0 if and only if x is equal to 0. Second condition, here inner product of xy defined a to be xt yt bar dt. So inner product of yx can be defined a to be yt into xt bar dt. Therefore, conjugate complex of both sides of this, that is yx bar equal to conjugate complex of a to b yt xt bar. This can be written as a to b conjugate complex of yt xt bar. Again, this can be written as yt bar and xt double bar, and xt double bar, that is xt. So xt and yt, that is scalar. So we can interchange the position. So integral a to b xt yt bar dt. So as per the statement of this example, we can write this is inner product of xy. So inner product of xy equal to conjugate complex of the inner product of yx. So second condition also proved. Third, let alpha is scalar, that is complex number, and xt belonging to CAB. That inner product of alpha x y equal to integral a to b. This is alpha x t yt bar dt. Okay, so this can be written as a to b alpha x t yt bar dt. Okay, so alpha independent of t, so we can write outside the integral. That is, this can be written as alpha into integral a to b xt yt bar dt, and this integral, that is inner product of xy. So inner product of alpha xy equal to alpha into inner product of xy. Third condition also satisfied. Fourth, let z belonging to CAB and xy also belonging to CAB as above. Okay, so inner product of x plus z y equal to inner product of x plus z t yt bar dt. Okay, so this can be written as integral a to b xt plus zt yt bar, that is integral a to b xt yt bar dt plus integral a to b zt yt bar dt. So as per the statement of this theorem, this integral can be written as inner product of xy plus inner product of zy. Hence the space CAB, that is order pair of CAB and given inner product, this is an inner product space. In this lecture, we have discussed the inner product space with some examples. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Naresi. Second, introductory function analysis with applications, John Valley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.